Ba't ganon?
Hayaang buksan ang isipan.
Sa science o agham, tayo na sa siniskwela. Tuklasin natin ang siyensya.
Buksan ang pag-iisip.
Tayo'y likas na scientist. Tayo na sa siniskwela. Tuklasin natin ang siyensya. Kinabukasan ng ating bayan, siguradong makakamtan. Sa daigdig ng agham, tuklasin ang kaalaman. Halina't lumipad sa daigdig ng isipan. Tayo na sa siniskwela.
Good morning, class. Today we will having an exam, and this is the problem. Okay, let's start.
A large stationary Brayton cycle gas turbine power plant delivers a power output of 110 megawatts to an electric generator. The minimum temperature in the cycle is 310 Kelvin and the maximum temperature is 1600 Kelvin. The minimum pressure in the cycle is 110 kilopascal and the compressor pressure ratio is 10:1. Calculate the power output of the turbine. What fraction of the turbine output is required to drive the compressor? What is the thermal efficiency of the cycle? These are the given. Brayton cycle. Minimum temperature T1 is equal to 310 Kelvin. Maximum temperature T3 is equal to 1600 Kelvin. Pressure ratios P2 over P1 is equal to 10:1. P3 over P4 is equal to 10:1. Power output W net is equal to 110 megawatts and minimum pressure of P is equal to 110 kilopascal. Required power output of the turbine W dot sub T, fraction of the turbine required to drive the compressor, W sub C over W sub T, and thermal efficiency. Equations used for isentropic compression and expansion. T2 is equal to the quantity T1 times the quantity P2 over P1 raised to R over Cp. T4 is equal to the quantity T3 times the quantity P4 over P3 raised to R over Cp, where R over Cp is equal to R over the quantity 7 over 2 times R is equal to 2 over 7. Ws isentropic, which is equal to delta H, is equal to Cp times the quantity T2 minus T1. W net is equal to W sub T minus W sub C. Mass flow rate is equal to W dot net over W net. W dot sub T is equal to mass flow rate times W sub T. And Q sub H is equal to Cp times T3 minus T2. In solving the given problem, the heat capacity of air is 1.004 kJ per kilogram Kelvin and assume constant throughout the process. Isentropic compression in the compressor occurs between the state 1 and 2 of the process. Again, we can say that the process is isentropic if compression or expansion of gas takes place with no flow of heat energy either into or out of the gas. With this, the value of S1 is equal to the value of S2. Thus, using the formula where R over Cp is equal to 2 over 7, S2 is equal to S1. Then, T2 is equal to the quantity T1 times the quantity P2 over P1 raised to R over Cp. Then, substituting the given in the formula, T2 is equal to 310 Kelvin times the quantity 10 raised to 2 over 7. T2 is equal to 598.5163 Kelvin. Consequently, isentropic work of the compressor can be computed using the formula W sub C, which is equal to delta H, is equal to Cp times the quantity T2 minus T1. Substituting the given to the formula, Wc is equal to 1.004 kJ per kilogram Kelvin times the quantity 598.5163 Kelvin minus 310 Kelvin. The value of W sub C is equal to 289.6704 kJ per kilogram. Moreover, between the state 3 and 4, isentropic expansion transpires in the turbine. At this junction, S4 has the same value of S3. T4 will be calculated using the formula T4 is equal to the quantity T3 times the quantity P4 over P3 raised to R over Cp. Then, substituting the given to the formula, T4 is equal to 1600 Kelvin times the quantity 1 over 10 raised to 2 over 7. Then the value of T4 will be 828.7159 Kelvin. Now, the solution will proceed to the calculation of the isentropic work of the turbine using the formula W sub T is equal to delta H is equal to Cp times the quantity T3 minus T4. W sub T is equal to 1.004 kJ per kilogram Kelvin times the quantity 1600 Kelvin minus 828.7159 Kelvin. Then the value of W sub T is equal to 774.3692 kJ per kilogram. The net work done by the system is equal to the sum of work of expansion has positive value and work of compression which has otherwise negative value. So, W sub net is equal to 774.3692 kJ per kilogram minus 289.6704 kJ per kilogram. Then the value of work will be 484.6988 kJ per kilogram. Solving the overall net and cycle efficiency, mass flow rate is equal to W dot subnet over W subnet. Mass flow rate is equal to 110,000 kg per second over 484.6988 kg per kilogram. Then the value of the mass flow rate is equal to 226.9451 kilogram per second. Solving the power output of the turbine, we will use the formula mass flow rate times the isentropic work. Then, substituting the given to the formula, the result will be W sub T or the power output of the turbine, is equal to 226.9451 kilogram per second times the quantity 774.3692 kg per kilogram. The result will be 175.7393 megawatts. Therefore, the power output of the turbine is 175.7393 megawatts. We will divide the work of the compressor to the work of the turbine to get the fraction of the turbine required to drive the compressor. Then, it will result to 289.6704 kg per kilogram over 774.3692 kg per kilogram. Therefore, the fraction of the turbine required to drive the compressor is 0.3741. Then, energy input is from combustion. The formula will be Q sub H is equal to Cp times the quantity T3 minus T2. Substituting the given to the formula, 1.004 kg per kilogram Kelvin times the quantity 1600 Kelvin minus 598.5163 Kelvin. Q sub H is equal to 1005.4896 kg per kilogram. Lastly, to get the thermal efficiency, we will use the formula power output over the energy from combustion. Then, substituting the values to the formula, thermal efficiency is equal to 484.6988 kg per kilogram over 1005.4896 kg per kilogram. Therefore, the thermal efficiency is equal to 0.4821.